Alright, so this is a short video to show you exactly what I want you to do to complete the simulation portion of the titration lab. So the first thing we're going to do is over here you see you can select the type of titration or type of reaction. I'm not going to talk about this difference between a strong acid strong base titration versus a weak acid strong base titration, but that's essentially what we're going to be doing here. So weak acid strong base, so select number 1, weak acid strong base. I want you to fill the burette with acid. So there you go. Now the acid, they only have one choice for the acid, so the acid we're going to use is acetic acid here. You can see the volume going up. And the base actually doesn't matter if you choose potassium or sodium hydroxide. We'll check sodium hydroxide. So the flask now will be filled with sodium hydroxide. So I will go through an example with a different type of reaction to show you kind of the details of how this works. But for right now, what I want you to notice, a couple things here. First off, you'll be doing a titration, so it's a weak acid strong base titration, right? So weak acid strong base titration. So that's number 1. Right? Number 2, fill the burette with acid. Now there's 2 ways to spell burette. You see it sometimes with 2 T's or 1 T, doesn't matter. Fill burette with acid, and in this case acetic acid. They give you the chemical formula here for acetic acid, CH3COOH. That's one way of looking at it. The way you might be familiar with is HC2H3O2, but this here is acetic acid. It's a weak acid. The indicator we will select here is bromethymol blue. 1, 2, 3. This must be 3, 4. Acetic acid, CH3COOH. Same thing. And sodium hydroxide. 4. Select the indicator. Bromethymol blue. That fills the burette, or fills the flask with the base. So bromethymol blue is blue in base. So bromethymol blue, the color here is blue in base, and you'll see a color change here when we add. Notice the concentrations here. These are concentrations here are constant, in the sense that they are not, well, it's going to be the same for each of your 3 titrations. The only thing that's going to change is the volume of acid that you add. So when you go to add acid, now I'll just add a whole bunch of acid here, and you see the color changes from that blue to yellow. So bromethymol blue is blue in base, it's yellow in acid, and so this is the end point. So that's what you'll do, and you'll do it 3 times. And so clearly I over titrated this, but if we were to do this a 3rd time, you're going to do this in triplicate. What you'll select then is, don't select reset, select concordant values. All right. So what we have here is acetic acid of unknown concentration, but if we select concordant values, the molarity of the base will be the same, as will the molarity of the unknown acid will be the same. So here we go. So notice the molarity of the base has not changed. Makes life a little bit easier for you. Then you can go ahead and do the 2nd titration. You should get numbers that are similar to the first, because of volume and molarity of the base. These known values are the same. The unknown, right, this is what we're determining here. What we're determining here is the unknown acid concentration. So we know it's acetic acid, but what we don't know is the concentration. So what we don't know is the amount of acid that we'll take, and then of course using the titration equation, molarity of the acid times the volume of the acid equals molarity of the base times the volume of the base, you will be able to calculate the molarity of the acid for each of your 3 trials, right? So the molarity of the acid is what's unknown. The volume of the acid is determined by experiment. And the molarity of the base, the volume of the base will be given to you. Now this should be the same for each titration so long as you select concordant values, right? Do not hit reset or you're going to end up having to start all over again. So just to give you an idea how this works, and you can play around with this as yourself, I'm going to select a strong acid, strong base titration, and I will select say sulfuric acid and sodium hydroxide, the burette with acid, and we'll use the same indicator here. Now the titration is different here because of the stoichiometry. Let me go ahead and write this neutralization reaction down. Right, so we have sulfuric acid, H2SO4, plus sodium hydroxide. This is a double displacement reaction, neutralization reaction. We talked about this in the past. And so these cations are going to switch places. Right? So what do we end up with? The sodium displaces the hydrogen. We're going to get sodium sulfate. Hydrogen displaces the sodium. We'll get HOH, or if you wish, water, H2O, right? So you get a salt and water. But notice there's 2 hydrogens here, only 1 sodium. So the charge on the sulfate ion is -2, and so we're going to need 2 sodiums to balance that. So if we have 2 sodiums here, we're going to need 2 here. Right? So the stoichiometry is it takes 2 moles of sodium hydroxide to neutralize 1 mole of sulfuric acid, and of course in the process we make 2 moles of water. So it's a 2-to-1 stoichiometry, right? I can say 1 mole of H2SO4 for every 2 moles of NaOH. And that's because each mole of sulfuric acid gives me 2 moles of, put it here, hydrogen ions, right? Now there is another unit of concentration that you sometimes come across when we're dealing with acids and bases, and that's normality. So there's molarity, right? We know molarity. This is moles per liter. And then there's something called normality, and you might see this on some reagent bottles for acids and bases. Normality. This is given by this uppercase N, not M, right? Molarity is uppercase M. This is normality, and this is moles, but it's not moles of solute, it's moles of equivalence. Formally, the term we use is equivalence. Moles of equivalence per liter. And what an equivalent is essentially hydrogen ions. So think about this. If we had a 1 molar H2SO4 solution, we'd have 1 mole of hydrogen sulfate, right? 1 mole of sulfuric acid per liter. That will give us 2 moles of hydrogens per liter, 1 mole of sulfur, and 4 moles of oxygen, right? Well, the equivalence is a hydrogen ion. So I just here hydrogen, H plus ion, right? So this normality kind of takes into account this stoichiometry. So a 1 molar sulfuric acid solution would be 1 normal. We use the term normal, like molar, molarity, normal, normality. So 1 normal, 1 molar would give us 2, this is a 2 here, would give us 2 normal, right? That's, if you wish, 2 moles of hydrogen ions per liter. Alright, so when we do this titration now, that's just a little background, so you have to take into account the stoichiometry. So when we do this titration, right, I don't know how much I'm going to add at first, and so I'm going to go maybe 5 mils at first, And then to actually add this, I'm going to press, so I just clicked on the slider, moved it up a little bit. I'm going to hit the dropwise. Right, so now I've added 5.02 milliliters. So you have to actually hit the dropwise to actually add this stuff. And you could add it dropwise by just keep clicking on this. Nothing seems to be happening here, so I'm going to go up another milliliter. So okay, maybe a milliliter and a half, and then I have to click dropwise again, and still nothing's happening. So I'll go up another milliliter. Oops, I went up 2 milliliters. Still nothing happening. I'll try to go up another. Try to go down. Oops, see, now I overshot it. Okay, so clearly 10 milliliters is too much, but that's the first one you can do, right? So you're gonna, in your report sheet, you'll write this down: 10.22 milliliters of acid. We don't know what the concentration of the acid is yet. We can calculate that. The molarity of the base, the volume of the base, that's not going to change so long as we hit concordant values. All right, so I'll press concordant values, and it took 10 milliliters last time, so this time I'm going to go up maybe 9 milliliters. Oh, 9.5 is still too much. All right, well, you can write down 9.52. Again, these values shouldn't change. Then I'll press concordant values again. All right, now this time I'll just go up 8 milliliters. Do it a little bit more carefully this time. I'm going to stop there at 7.5. Now what I can do is just keep hitting the dropwise until one drop makes it change colors. Okay, I'm at 8 milliliters. It should be 8.0, but 8.02, now I add another drop. So remember, these burettes are read to 2 decimal places. This isn't the best simulation. It would be nice if they had the color change a little bit, like you'll see in those videos where they're using phenolphthalein, and when the drop hits, it turns red right away, but then the red disappears. Here we don't get that, so we're kind of driving blind a little bit here. So that's why I'm going so slow. Okay, we're getting up to 9 now. It took just a little over 9 last time to see what happens here. So that 9.5 must have been pretty close. Let's see. There we go. It turns green. So this actually would be the endpoint, right? And we'll talk a little bit about the endpoint in just a moment. But it turns green, and one more drop. Oh, one more drop. You can write these down: 9.48, 9.5. There we go. 9.52. Okay. So I have. Do the math now. So it was 9.52 milliliters. That's the volume of the acid. Remember, the molarity of the acid we don't know. The molarity of the base, 0.1482. That was the same for each one. 0.1482 molar. The volume was the same each time, 25 milliliters. So you can calculate the molarity of the acid. Except I'm going to cross this off. Remember how we talked about normality? This is actually normality of the acid, and the reason for that again is because sulfuric acid is diprotic. So when I do the math here, it's going to be 25 times 0.1482 divided by 9.52. Okay, I get 0.3892. 0.38, that's an 892, and this would be normal. So 0.3892, this is normalty. Again, that's what? Moles of hydrogen ion, hydrogen ion, not hydrogen element per liter. Remember to go to 4 decimal places, right? Well, actually, it would be 3 decimal places because the volume here of the acid is just 3 decimal places. So 0.389 would be fine. But this number is actually twice the concentration in molarity. So when they're asking for the molarity here now, I'm going to have to divide by 2. So divide by 2, what do I get? 0.19445. So I'll round off to 0.195 molar. And this is molar sulfuric acid, H2SO4. Remember, each mole of sulfuric acid is going to give us 2 moles of hydrogen ions, so that's why I talked about normality here. Now for your titration, we're using acetic acid and sodium hydroxide. See, it's a 1-to-1 stoichiometry. You don't have to worry about it. But let's just see if I did this right. We can put these numbers in here now. 0.195. And hope that's right. Yes, correct. And actually gives you a graph here. We don't have to worry about the graph. Right. So that's what you'll do for the titration, but again, you'll be using the weak acid, strong base, acetic acid, sodium hydroxide titration.